Welcome to our second webinar series, First Steps, New Replacement Part Castings Made from Old Drawings. This is part one of a four-part series. My name is Joya Speaker, and I am the team lead for the American Metalcasting Consortium's Castings Advanced Systems Technology Integration Team, also known as CAST-IT. This seminar is funded by the Defense Logistics Agency and has been developed by CAST-IT to assist DLA suppliers in successfully supplying these complex cold start legacy castings. Our first webinar series, titled First Article Approval Success, How, Who, What, and Why, covered why first article approval for any casting is difficult, but especially for these legacy castings that are produced as cold starts by new awardees. We addressed that many facets are needed for success among 3 to 5 separate businesses, and who is responsible for what. We also discussed that dimensions are by far the most challenging facet. So what can be done about that? Finally, we talked about how castings have surface anomalies that are unavoidable and part of the casting, molding, and finishing processes. So how can those be accommodated and we still meet dimensional and surface appearance specifications? Our bottom line secret for first article approval success is collaborative and intentional manufacturing engineering of the processes and all of the tooling among the separate business partners. We have the metal caster who may be the awardee, or the machine shop may be an awardee. We also might have a heat treat partner as well as a coder. At the center, highlighted in green, is the mold cavity tooling builder, who plays a vital technical role in the success of first article approvals. They have the software experience needed to create the tooling, as well as the GD&T expertise to understand what the drawing intends and how to convert it to a solid model, 3 of which are required to make not only tooling, but the fixtures and other mold cavity making and finishing and processing. And finally, the way the mold cavity is made today can include significant additive or subtractive manufacturing techniques. It is the mold cavity tooling builder who has the access to those technologies and can make the mold cavity much more likely to be approved dimensionally with these techniques. Given the complexity of a cold start first article approval by a new awardee who is often a machine shop, a simple first step is an introduction to the metal casting industry terminology. That is our subject for part 1. Part 2 will discuss how and with whom to partner. With as many as 5 separate businesses collaborating to make a finished legacy casting who may not even know each other, how does the awardee choose? Part 3 will consist of case studies of how to succeed. Pathways of the complexities outlined in Part 2 will be illustrated. Part 4 will address the collaborative manufacturing engineering among the machine shop, including a fabricator in some cases, the mold cavity tooling builder, and a metal casting, to arrive at an approvable net shape that is 80, 90, and even 95% as cast, which is a net shape that has very little machined or fabricated. So what would be the machine tool choice to be most efficient with such a high percentage of as-cast surface? And what would be the fixture design principles for consistency of setup as well as the least number of setups to maximize the benefit of as-cast surfaces? So that you as an attendee can interact with our team's presentation, I will enable a chat box now so you can document your questions, comments, and any discussion points as the webinar progresses. At the conclusion of the presentation, I'll return along with the rest of the CAST-IT team for a Q&A and discussion. Now, leading us off is our teammate Gary Burrow. Gary is one of those mold cavity tooling builders who is well respected at the high end of those green colored capabilities you saw in the earlier diagram. Gary will lead us off with a primer on basic metal casting industry terminology. Then he'll go into some additive manufacturing technologies that enable mold cavity designs by cold starts to be successful in first article approval. So without further ado, here is Gary Burrow starting us off for part 1.
Hi, I'm Mike Gwynn, 20-year teammate with Gary, who couldn't be with us at the moment, but who will join us for questions and answers at the conclusion. I have Gary's notes, and I'm going to speak to you as though I am Gary. It's a privilege to step in for Gary, and a bright spot from your standpoint is that Gary and I do exactly what Webinar 1 and this Webinar 2 profess. That is manufacturing engineering of all the tooling and the mold cavity making process to achieve first article approval. In the roles we've been speaking about, the typically 3 separate businesses that have to collaborate for manufacturing engineering success in launching any casting, but especially DLA legacy castings, Gary is the mold cavity tooling builder, and I'm the metal casting producer. Right now, the two of us are doing exactly that on a complex Air Force casting. Although I'm not producing castings anymore, I'm contributing to manufacturing engineering as though I were. So here I go as Gary. I'm Gary Burrow, 4th generation pattern maker, having built tooling for a wide variety of metal casting alloys and mold making processes, including additive and subtractive manufacturing. Originally located in Southern California and now Montana, H.A. Burrow Pattern has built tooling for casting molds and casting processing in aerospace, military, and commercial applications. Now, I am frequently a turnkey source for low-volume replacement castings for both the Defense Logistics Agency and out-of-production commercial equipment. Rather than my traditional name, pattern maker, a better descriptive term might be mold cavity making tooling builder. Not just a pattern for a traditional mold process, but also mold elements printed by additive manufacturing and then inserted into that mold cavity. As pointed out in Julia's introduction, I am the separate business colored in green that can integrate the manufacturing engineering of a cold start new casting to replace castings in old systems long since out of production. Sometimes a metal caster or a machine shop choose me to help them, but increasingly I hold the contract and I choose them. So now let's talk about metal casting terminology. First, let's define some terms. Mold, expendable molds used just once. Those are made in sand, plaster, and ceramic, and they're applicable to any alloy. There's another kind of mold just used repeatedly or used repeatedly. Those are tool steel permanent mold, tool steel die casting dies, and they're applicable to low temperature alloys, generally zinc, aluminum, and magnesium, and with special methods they can be applied to copper-based alloys. A pattern. A pattern is a hard material that forms the shape of expendable molds. Wood, plastic, cast iron, steel. They can be cast, machined, or printed via additive manufacturing to final shape. At the lower left, we see a machined cast iron tooling for the resin shell process, and we see a traditional wood pattern being constructed at the right. Dies. Die type 1 forms softer material into the shape used in expendable molds. Wax for ceramic shell investment castings, and styrofoam for lost foam castings. The dies are usually machined from aluminum. So at the lower left, we see an operator wax welding golf club patterns to an investment casting tree, and at the center and at the right, we see the lost foam patterns made from a die for an engine block, or those are engine heads. Die type 2 is high alloy machine to form mold in the die casting and permanent mold processes. So here we see a picture of 2 halves of a high alloy steel machined die for the die casting process. Won't go into the details of it, but you can see that there's a lot of complexity in the way the die not only is formed, but also the way it's actuated, that there are cooling lines on one side to help the solidification integrity, and chills, whether they be water or whether they be metal shells and sand molds, are an important part of the metal casting process. We'll know more about chills in an upcoming couple of slides. A core box, a box shaped that surrounds a cavity. The cavity is filled with sand along with a sand grain binder that makes a strong mold element that forms cavities inside the casting or along its exterior walls. So at the lower left in white, we see 2 halves of a box that forms the core at the lower center. The core itself bridges across 2 ends of the casting mold, and the extensions that are at the end of the core feature are called core prints that enable them to sit in the mold and bridge across an area to create a hollow cavity in the casting in that particular case. In the center is a metal core box, and at the right is a more complex metal core box with multiple pieces and an ejector system for the core. Well, here's more about cores. Sand mold elements that form an internal cavity in the casting, as we have discussed, but can also form external cavities along an exterior wall, can form the entire casting exterior surface, or in assembly with other cores can form the entire mold. So here's some examples. At the lower left is a huge volute pump being formed in a pit, and you can see a man down inside the center of the mold receiving these core elements from a crane up above and assembling the cores into that mold to form the volute pump shape. At the center at the bottom in the multicolors is a very complex assembly of cores that forms an entire engine block, and that assembly of cores forms all the interesting geometry of the engine block and then is set in just a simple green sand mold, which provides the mold cavity delivery, the metal delivery system into the complex geometry formed by the core. At the lower right is a cover core that's used sometimes in sand molds to either create a bottom gate situation, which is what we see going on here, or to make a more complex upper or lower portion of a sand mold that the regular sand mold process couldn't make by itself. And at the upper right are three different kinds of cores in assembly in a mold, and we'll talk about those in a moment. A slide is a mechanized mold element that's an equivalent of a core in metal molds like dies, like a die casting die that's shown here. And the slide extends and retracts into the mold to form the geometry and then retracts to enable the casting to be ejected from the mold. At the lower right is a picture of the complexity of a die casting die that has slides moving in and out in 4 different directions. A parting plane. A parting plane separates the mold so that tooling can be extracted, leaving the overall mold cavity split into 2 parts, usually 2 halves. So at the upper center, we see a solid model showing an offset parting plane that enables a cylindrical feature at the right end of the casting to be formed without a core. At the lower center is that casting that we've already seen once, and if you look at that green line from the center left on down through the middle portion of the casting, up and around and over to the plate part of the casting, is what we call an offset parting for a sand mold to create that mold cavity by using the geometry of the parting plane to eliminate cores. Match planes. Match planes separate elements of the mold between the mold cavity itself and from cores to themselves. So here we see that same casting now with 3 different types of cores that have match planes associated with them. The little button core at the bottom forms a little hole in the plate section and has what we call a flower pot core print that sits in the drag, and then the cope fits over the top of that, creating that hole in the plate. At the center right, we see what we call a bootjack core, which forms another hole along the side of the casting, and the bootjack portion of it takes the core up to the parting plane so that the core can be set in the drag, closed over with the cope half, and not leave a portion of empty space for the metal to fill in where we don't want it. In the upper right is an assembly of resin shell cores, which are very accurate, making the datums and the hole positions of an axle seat assembly for this suspension component for a Class 8 truck accurate enough to not be machined. Draft. Like a cupcake pan, draft is a slant on a mold cavity feature that enables the cupcake to get out of the pan. Except for mold cavity elements printed by Additive Manufacturing, all of them have at least a little or a lot of draft somewhere. The genius of mold cavity process choice, and basically that's what I do, is help the metal casting producer with the mold cavity process and the way I design the tooling so that we put together collaboratively the draft on the surfaces where it won't bother the final net shape of the casting functionally or structurally, and help meet dimensional requirements by not having draft aggravating the linear tolerances that are specified in some cases where draft would upset the amount of tolerance that's allowed on a linear dimension. So tooling design along with the mold process choice is a very important aspect of accommodating draft so that you can meet primarily dimensional capability. Well, what does draft actually look like on a casting? Well, here we have a casting at the left, which is shown in gray, and we have a dotted parting line through the center of the casting. Although we express draft in drawings as an angle, it's not really an angle. It's better expressed as a draw length, which in this case is from the center of the parting plane on that casting, where the dotted line is, to the top and to the bottom. And that's the draw length. And as a consequence of the parting plane being in the center of the casting, the offset for each half of the draft is relatively small. But if we put the parting plane at the bottom of the casting and create all of that casting up on the cope side of the mold, well, then our draw length is twice as long and our offset is twice as big. So it's not really the angle that really we have to control for the sake of dimensional compliance, it's that offset. At the right is a chart that shows the offset amount that's required for differing draw lengths for different mold cavity tooling processes and different types of tooling for those mold cavity making processes. Mold degrees of freedom. This is important for dimensional capability. So we have basically a base tolerance capability for all of the different mold cavity making processes. And that base tolerance capability is achieved on one side of the mold, typically on the drag side of the mold. So in our picture here, if you could imagine a dimension from the left bottom half of that casting over to the center area, which is the other end of the casting, that was important. Well, all of that dimension was formed in the lower part of the mold, one part of the mold only, and that would be our nominal dimensional capability. And in our table that you see, that would be a mold-to-mold dimension, and our factor for coarsening or improving the mold, the tolerance capability would be 100%, or 1.00 times the process capability of that dimension given that process. Well, you can be more accurate across a core based on the fact that the core making processes are more accurate. So if we had an important dimension across that large core that's encircled in green, well, then the dimensional capability there is actually better than nominal and would be 90% of that particular mold cavity making process capability, in this case, air set sand. But if we cross a parting plane, or even more, if we cross a parting plane and have a core involved, which is what we have circled in our table down below, well, then we coarsen our factors significantly as far as what our mold accuracy capability is. So circled above, you can see in the mold, we have a core that stands tall, set in the drag and closed over in the cope. There's a lot of process variation and tooling degrees of freedom involved in all of that. And so now, whatever our best capability is dimensionally for a feature that involves that core and going across a parting plane, we have to coarsen our tolerance capability by 150%. So mold degrees of freedom are another area where the mold cavity tooling builder can use his choice of how the tool is constructed to maximize the mold to mold and core to core kinds of dimensional capability and minimize the degrees of freedom. Not everywhere, but where the dimensions are most critical. Contraction away from mold cavity walls. Well, traditionally, metal casting industry term for this contraction, which occurs after a casting has become solid, it begins getting smaller. It's not solidification shrinkage, but it is a dimensional shrinkage that occurs in the solid state. Well, when we were building tooling with wood and plastic before the advent of solid models and making tooling directly by additive manufacturing, subtractive manufacturing techniques from those solid models, pattern makers like myself had what we called a shrink rule. So if I was making a steel casting, I would actually have a ruler when I was making the steel casting that was 1/4 inch too long for a 12-inch dimension. So if I had an 18-inch ruler at the 12-inch mark, it was really 12.25 inches long, so that I didn't have to keep calculating the dimensions as I was building the tooling. I had the shrinkage rate built into my rulers, and that's why we called the contraction problem that we have with all metal casting alloys the shrink rule. But actually a better term is pattern maker's contraction, because we're building that contraction rate now into the solid models. We're not using rulers and hand construction of tooling anymore. And so therefore the size difference is built into the solid models from which the tooling is constructed. Well, what's the issue with this? Well, it varies a lot. It not only varies within any particular alloy, like in this case, it's that 1/4 inch per foot for carbon and low alloy steels. You can see how much it varies with dimension length, and it varies with the red and green blue dots based on the type of binder system, and it varies with the mold geometry, how much the mold constrains that contraction. So guessing at it is a big issue, because all of the dimensions on a casting are the result of a guess as to what that rate is actually going to do, and you can see the variation that we suffer with. Here's a table that shows the contraction rate. Center column is the best because that's the rate per foot for the different alloys among the families in the spectrum of metal casting alloys. And you can see that across the spectrum of metal casting alloys, there is a lot of variation in the contraction rate. So in the old days, I had to have a different ruler for all these different alloys. Even if I was making copper-based alloys, I'd have to have a different ruler for different copper-based chemistries among the copper-based alloy families. Well, now, of course, we applied all that through additive and subtractive manufacturing techniques and from the solid models, but I still have to guess at it. So that means that when the casting is made for first article approval, if we don't make some prototypes quickly to evaluate my guess, which I should make collaboratively with someone like me, the metal casting producer, then we're likely to have more errors on my guess than we can live with, and we have to do a lot of rework of the tooling to make the dimensions come in. It's not that the dimensions aren't accurate enough, it's because the guess is wrong and the dimensions aren't centered within their tolerance band. This big issue. People wonder, why can't we get the dimensions right on castings? Well, there you go. This is it primarily. Gating and risering. Gating and risering is the metal casting industry's shorthand for attachments to the casting's geometry to fill the mold with liquid alloy, vent the air and combustion gases, and set up temperature and mass gradients to meet the solidification integrity required. Solidification integrity is important because that's where the mechanical properties like yield strength and elongation percent come from. Runners, ingates, vents, chills, risers, or what we could call, in total, process interface geometry. At the upper left is an actual DLA legacy casting. It's a cover for a shipboard machine gun and accesses the internal portions of the machine gun mechanism. It's a relatively simple casting, but you can see that there's a considerable amount of additional geometry added to deliver the liquid metal and to feed solidification shrinkage. And you can also see in yellow at the bottom a core that forms a handle for access in removing that cover from the machine gun housing. Well, those cylindrical features are risers to feed solidification shrinkage. Those have to be removed, and when they're removed, they're not going to be as accurate as the adjoining mold cavity surfaces. So as we talked about in webinar 1, the attachments of process interface geometry are not as accurate as the mold surfaces themselves, which don't have the removal and the light grinding that goes on with creating smooth surfaces as if those risers and ingates were not attached. But let's look at a more complicated situation at the upper right. So in gray is a low alloy steel casting, and the green is the liquid metal delivery system. The vertical portions in the green are the risers to feed solidification shrinkage. And if you look closely at the upper center, you'll see a yellow feature, which is a metal chill set in the sand to help cool that block at the upper end of the casting, which is thicker than the rest of the casting, and that chill helps set up temperature and mass gradients to get better solidification, because that's an important structural part, high stress part of this casting. And then at the center bottom, we see the venting of gases from a low alloy steel casting. In this case, we're looking at 2950 Fahrenheit as the pouring temperature, and the combustion gases from all of that temperature are very large, both in pressure and in volume, and need to be evacuated real specifically with a venting system design in the right places and the right size. The casting, as in the upper left, although it needs to be vented as well, has a pouring temperature of probably 1325 Fahrenheit, and so therefore the immediate combustion of mold cavity binder systems and creating gases quickly with large volumes of pressure is not nearly as great. Well, what does gating and risering or process interface geometry do? In the liquid metal delivery, you can see that the strategy is to provide primarily temperature gradients, and you can see the effect of that chill at the upper end turning blue much more quickly. Let me run it again, and I'll explain more as we watch again. But watch at the upper left and how quickly the blue forms from the chill that's underneath the mold cavity in the sand. But the idea of gating primarily is to create the temperature distribution that favors the solidification gradients needed for the solidification integrity that results in the mechanical properties that are specified. The risering is attached to provide reservoirs of feed metal to feed solidification shrinkage inside the cavity, and essentially take the shrinkage that's occurring inside the cavity and transport it out of the casting and into the riser itself, where it can be cut off and remelted. So then, therefore, you're exchanging the shrinkage that occurs inside the casting for the volume of the risers, where the shrinkage can reside and not hurt anything. So let's look then at what the solidification of the casting looks like with this gating and risering strategy that we've now seen. So here we're looking in these blue and purple areas, primarily the critical fraction solid, which is essentially a mushy zone of combination of liquid and solid going on at the same time, in which it's critical because at a certain point the casting can still feed itself to solidification integrity at that critical point. So we're looking in the blue particularly at that time in which the feeding of the casting is at risk for getting too solid and not enough liquid in the mush. So those two blue spots that we see in the interior area, which is another high stress area of the casting, is in question. We want to make sure that those blue areas disappear as the casting continues to solidify, so that we have high integrity solidification for the mechanical properties that are going to be necessary in that high stress region in the center of the casting. So let's see how that plays out. And you can see those clear up nicely. That critical fraction solid at that point was great enough that we were able to feed those little blue spots to solidification integrity nicely, and didn't have solidification shrinkage problems that would affect the mechanical properties. So bringing these terms to life, we have two videos coming up. The first one is the sand mold process, and we'll summarize many of the points and the terms that we have been discussing. And then after that, I'll come back to you. We'll talk a little bit about some of the principles of the investment casting process, and then we'll see a nice video of that. And then finally, we'll wrap up with the technologies of additive manufacturing, which are such an important part of what I do in mold cavity tooling design and construction. So here's our first video for the sand process.
Here's a well-done animation of horizontal sand molding, typical of green sand or air set. It shows how the mold cavity is created, how the casting is poured, removed from the mold, and processed into final shape. The inset shows that the casting is an elbow for fluid flow. That means that the casting is hollow, and the hollow portion of the casting is formed by a core. The core is made in a tool called a core box in two halves in this case and pasted together. Then the mold has two halves, an upper half and a lower half, and the core is set in the lower half and closed over. Now we see addition of a gating system and risers to feed solidification shrinkage. In reality, this process interface geometry is highly engineered to meet the casting's class and grade specification. Horizontal sand molding, the top half of the mold is called the cope. A box or flask is placed around the pattern and filled with sand. The drag is the bottom half, and the core is set in the drag. When packed, the sand conforms to the shape of the pattern with a binder mixed onto each sand grain. When the top and bottom halves of the mold are fastened, the mold cavity is now complete. Now we're seeing a cutaway view of the mold cavity and a simplified concept of how the mold cavity is filled. The inset shows a stainless steel valve made in sand, as it really would be, with the cored hole, and the mold filling sequence shows how the engineering of the liquid metal delivery is part of the way the solidification for integrity of the valve is established. So this representation of a horizontal sand mold is what it would really look like. Metal casters call this sequence finishing of as-cast surfaces. Note that the cutting off and blending of the process interface geometry, gates, and risers is done by hand. Some dimensional capability of the mold itself is coarsened. Finally, the machining and/or fabricating on a casting to reach final net shape is always small compared to other metal shaping processes. Castings are always mostly net shape as cast, sometimes 100%.
Our next video is for the ceramic shell investment process, and it's a more complicated process, so we'll take this diagram of how the process works to give you a preview so that you can understand the video a little bit better. At the left side, we see wax patterns assembled on a tree. The wax patterns have the shape of the ultimate casting, which in this case there are 6 of them. And then those wax patterns are invested in a pre-ceramic powder along with a liquid pre-ceramic binder system to create a buildup of a shell around the wax patterns. Then the wax is melted out of the assembly of the pre-ceramic mold, and that's why we call it lost wax. So we invest the wax in the pre-ceramic powder and pre-ceramic binder system, and then we lose the wax by melting it out in an autoclave. And then finally, we preheat the mold in a firing furnace, just like you make ceramics in a kiln, the same idea, and the mold becomes ceramic, and while it's still hot, then the alloy is poured into the mold, which has some advantages for some alloys to be poured in a hot mold. So some of the examples of that process are the fan frame, a large titanium casting at the lower left with veins being wax welded into the pattern. There's a powertrain casting at the center left, which has all of the gear features, the worm gear, the spur gear, the hex to drive it, and so on, are all as cast without machining. Some more complicated castings, as an example there in the center and center right, but then a casting that I made with the Army, which was kind of a breakthrough casting, an example of why the hot mold can be really important. This is a 17.4 pH high alloy steel with a 2 millimeter wall thickness on that curved plate section over about a 500 millimeter length. This basically unheard of in low alloy and high alloy steels to be that thin over such a long curved feature. But the hot mold was one of the ways that that thin wall feature was accomplished. So let's take a look at the video now of how it actually works.
Let's take those steps in the ceramic shell investment process and bring them to life with an animation. First, we have that die that creates the wax patterns. Wax is warm and slick, So it will release from the aluminum die with minimum, sometimes no draft. However, there is contraction in the wax and ultimately contraction in the alloy when poured. So there are two contraction rates that have to be designed into the tooling, and pattern maker's contraction is a concern in the design of the tooling to make sure that the dimensions, although extremely accurate, are centered within the specified tolerance band. In addition to the accuracy of the ceramic shell investment process, the complexity of castings that can be made in the process is very significant. We see here a wax pattern that has many complexities and fine detail in its structure. This inset shows the complexity of the aluminum tooling to make that wax patterns. An upper and lower half with slide mechanisms coming in from the side to create the cavities in the exterior profile. Next, the wax patterns are attached to a central wax bar called a sprue to form a cluster or tree. This inset shows an actual cluster or tree with 4 red wax patterns in the foreground and 4 more in the background. We'll follow this cluster along with the video in each step of the process. Next, the tree is dipped or invested into a slurry of pre-ceramic binder, drained and coated with a fine ceramic refractory for a fine surface finish against the wax. After drying, this process is repeated with progressively coarser refractories until a self-supporting shell or mold is formed. Continuing with our tree or cluster of 8 patterns embedded in a wax process geometry, we see a robotic arm dipping the tree into a slurry of pre-ceramic binder and evenly coating the entire interior profiles of the tree with the pre-ceramic binder. Alternately, the dipped wet tree or cluster is coated with ceramic particles, dried, and then the process is repeated, building up then a pre-ceramic shell, which is thoroughly dried before further processing. After the tree or cluster is thoroughly dried, it is heated, usually in an autoclave, to drain out the wax. The reclaimed wax is used for other trees and vents in the cluster, and new wax is used for the patterns. Next, the empty tree or cluster is put into a furnace and fired at high temperature to remove all residual traces of wax and take the pre-ceramic shell and turn it into a ceramic. The now ceramic shell is removed from the furnace and poured while the shell is still hot. Depending on the alloy and the fluid life of the alloy, pouring the shells while they're hot is a tremendous benefit for filling in thinner sections, thinner walls, and fine surface detail. Finally, after cooling, the ceramic shell is removed from the casting by mechanical vibration, chemical cleaning, or water jet blasting. After the ceramic shell has been removed from the cluster, it is shot blasted, and then the castings are removed from the cluster, usually with a bandsaw.
Additive manufacturing for sand and investment casting molds, which, as we have seen, those two mold cavity making processes are the most logical for the dimensional capability and integrity required for legacy castings, particularly legacy aircraft castings for DLA. As part of my turnkey role as a mold cavity tooling builder, I often deploy additive manufacturing to improve the accuracy of the mold cavity that I'm designing for the overall manufacturing accuracy of the as-cast surfaces. Most of those as-cast surfaces are final net shape, and as we'll see in part 4 of this series, that castings have high percentages of net shape that are as-cast, typically more than 80%, lots and lots of times more than 90% are as-cast features net shape. So only a few are upgraded by machining, so it helps me to use additive manufacturing technologies to make the mold cavity more accurate for those final net shape as-cast results. When I'm leading the effort for a legacy aircraft casting with complex geometry, I choose printed sand mold elements to improve the accuracy of air-set sand molds, or I choose one of two additive manufacturing technologies to directly print wax-like patterns for the investment casting process. The reason for this choice is the combination of complex geometry and especially tight dimensional tolerances. Unless the TDP specifically requires a sand casting, both options are acceptable for first article approval success, and the choice depends on the overall dimensional accuracy required. The choice may also be based on two other factors: avoiding a machine surface, surface finish, or both, a surface sufficiently smooth and dimensionally accurate. The best way to illustrate additive manufacturing options to improve mold cavity accuracy is through pictures. We'll look at two options for sand mold first: hybrid mold cavities. Primarily made with patterns and cores in the usual air-set molding process, but the hybrid part comes when we add printed mold elements to the mold cavity that don't have draft or other mold assembly degrees of freedom. Entirely printed mold cavities assembled is another option. So here's a picture that illustrates the process for the hybrid traditional air set plus additive manufacturing. So here is an operator setting chills in the drag half of an air set mold. So he's not setting additive manufacturing elements in there, but this is a picture that I found that illustrate what the assembly of the additive manufacturing printed mold elements would look like. So the operator is setting a chill in this case, but could be just as well setting additive manufacturing elements into the mold cavity as well. And those additive manufacturing elements would be like you see with the green arrows emanating from it, a kind of grayish green color element that has been printed from the loose sand that surrounds it. That loose sand is unbonded, and the greenish gray has been bonded with a printing binder system. So that mold element could be set in the mold just as the operator setting that chill, or it could be set in the mold above that open drag half there. So that's essentially the way the printed mold elements go into the molds, just like a core would or just like a chill would. At the bottom right is an assembly of many printed mold elements made in one large machine. Again, the white sand is unbonded and the grayish green color is bonded with a binder system that's printed and combines the adjoining sand grains together with the strength just like a core, very much like a core, just made entirely differently, directly from a solid model without tooling. The second option is an entirely printed additive manufacturing mold cavity. So here we see an intake manifold for an internal combustion engine. At the left, we see the drag half or the bottom half of what would be an air-set sand mold, but in this case, that entire drag half of the mold has been printed in this process. And then cores have been assembled on top of that to form the passageways of the intake manifold, the casting being shown at the right. Now let's look at two options for investment casting molds. SLA Quickcast uses the original stereolithography apparatus, that's where SLA comes from, technology, to print a white light setting polymer into an investment pattern directly from a solid model. The following picture sequence will explain how and why it works so well. So here is a 54-pound, 17.4 pH stainless steel investment cast housing that I produced. It wasn't a legacy casting, but we made 6 of those as sample casting using the SLA Quickcast disposable patterns to prove out the design. And then later we used wax aluminum tooling to make wax patterns in the traditional way to make 75 production castings. But those first 6 made this way are very much like what we would do and what I do often with the investment casting process to make DLA legacy castings. So at the left we see the solid model. In the center we see the printed SLA polymer, and at the right we see the resulting casting. Well, how about the economics of additive manufacturing for improved mold cavity accuracy? Well, continuing with our assumption that our cold start new awardee is a machine shop, with only an 8-day bid window, it's highly unlikely that a mold cavity making process beyond sand mold was identified in the proposal. As we've seen, the two most logical mold cavity making processes for legacy weapon system castings is air set sand and ceramic shell investment plus additive manufacturing for either process, perhaps. The two basic processes are significantly different in cost. The ceramic shell investment process is more costly. Having proposed cost already and probably not based on the investment process, when and why would the investment process be the overall lowest cost choice and remain inside the machine shop's cost proposal? Well, here are generalizations about the cost basis of that choice. The basic air set sand process applies well to DLA's land and maritime legacy castings, as well as to aircraft castings of simpler geometry, and it's the most economical. The cost drivers for air set sand molds are: one, complexity of the tooling and its amortized cost, and the required alloy. There are significant differences in the cost of molten alloy ready to pour across the metal casting spectrum of alloys. Making hybrid air set sand molds with additive manufacturing printed mold elements is incrementally more costly, but a good value for first article approval success when dimensional tolerances are tighter. Well, now generalizations about the ceramic shell investment process. The process itself is the primary cost driver. Alloy poured is a factor, but not major as it is with sand molds. Dyes for traditional wax patterns amortized into the cost is a factor also, but again, not major compared to the process itself. Additive manufacturing direct printing of wax equivalents is fairly cost neutral. The major benefit is more accuracy. Even the small draft offsets in dyes are not necessary. And speed. Excellent for quickly checking pattern maker's contraction, so adjust the solid model and try again. And in the case of printing, adjusting the solid model and printing again is really quick, especially for complex aircraft legacy castings. Even though the cost of the investment process was not anticipated in the cost proposal, the probability of first article dimensional success is much enhanced. The huge cost of first article rejection is much less likely. And again, quick checks of pattern maker's contraction and solid model adjustments are convenient and very quick. So with that, now here's Julia, and she'll set up the chat box for questions and answer and the real live Gary.
All right, so good morning, everyone, and thank you for joining us for our part one of the First Steps webinar series. So as Mike said, my name is Julia, and I'm the Cast It team lead. So while the rest of the Cast It team is getting their cameras turned on for the Q&A, I'll just take a minute and introduce a little bit about what we do. So Cast It is a team of application engineers, and we work to solve both technical and procurement problems regarding castings. So just want to point out a couple of resources. If you look in the handout section of the GoToWebinar control, you'll see a few handouts I've put up there. One is a Cast It one-pager that just goes over some of the types of projects the team's worked on, and as well as links to resources that we've put together on a wide range of casting topics. You also have the Casting and Forging Assistance handout, which covers different ways we might be able to help you and how to engage our team. And then last, there is a flyer with information regarding part 2 of the webinar series, which will cover how and with whom to partner. I know sometimes downloads are blocked by people's security, IT security, so I will be sending this information out after the webinar as well. So without further ado, let me introduce the Cast It industry experts, and we'll get started on the Q&A. So we have Gary Burrow is a 5th generation pattern maker and all-around casting guru. Dave Powlite, who doesn't have his camera on, is the VP of Technology at Steel Founders Society of America. And we have Mike Gwynn, who is a casting design expert. Dick Diano, who is an expert in all things 3D data. Keith Sturger, who is a metallurgical engineer, who's an expert in all things DLA and government processes. So combined, Castit has over 150 years of experience in the metal casting industry. So a lot of great knowledge with everyone. So it looks like we do have a question, and feel free to keep adding to the questions list. Gary, I think this will be a question that is good for you. So you mentioned eliminating draft on critical dimensions with mold cavity tooling design. How do you do that?
Well, basically, you can do it multiple ways. You can try to orient the pattern in the mold to eliminate those draft areas. You can also do things like add cores that create a no draft condition. So you put a lot of draft on the outside of the core, so you can set it in the mold, and where it kisses the part, it actually has a zero draft surface. That's typically only a problem in sand casting and investment. You can pretty well get away with no draft in that, because the wax tends to shrink slightly and it has some good lubricity to extract from the mold.
All right, great question and great answer. All right, and then it looks like we have one more. So the gating that was in the examples is pretty elaborate, and also it looked like it made the mold larger and reduced the amount of metal that ended up being a casting. Does that increase the cost? Mike, do you want to take a stab at this one?
Yeah, sure. Yes, it does. It does increase the cost, and there's two aspects of the cost that are increased. One is you're pouring more metal. Now, the metal that you cut off and remelt is a smaller fraction of the cost that ultimately winds up in the price of the casting. So it's incrementally a lot less than the cost of the casting itself to pour extra metal. And sometimes you do have to have a larger mold to accommodate the gating system, or even have cores involved in the assembly of the mold to accommodate elaborate gating. But the main point is that we're after solidification integrity, because the elongation percents especially, and to some degree the yield strength, which is specified for the casting, comes from that solidification integrity. And setting up the temperature distribution with that gating is a big deal to achieve that solidification integrity. And also, we didn't mention, but you can eliminate non-metallic inclusions with the gating system as well. So overall, it is a little bit more costly, but the cost benefit in finishing and getting approval for mechanical properties is well worth it.
All right, thanks, Mike. All right, so it doesn't look like we have any more questions, so we can go ahead, I think, and wrap it up. So thank you everyone for participating in today's First Steps webinar. We do value your feedback a lot. A brief survey is gonna pop up immediately after you close out of the webinar, so we'd really appreciate it if you take a minute to fill that out. In addition, if you have any questions about the content covered or any of the resources provided, feel free to reach out to me, and remember to register for part 2. All right, thanks everyone.
Thank you.